There you
Hi everybody, we're going over exponential functions. Today our objectives will be to be able to graph exponential functions, know the effects of multiplying numbers to an exponential, and to be able to take apart a word problem. So up to this point, we've gone over functions like y equals x. Um, these have a base of x, which is any real number, and an exponential of 5. Exponentials, on the other hand, are going to be following type y equals bx, where x, or where b is any positive real number and x is an exponent. So let's go over an example.
select the pointer or hit, select it, and now go up to the X.
So
There you go.
So we are going to look at y equals x to, or 2 So 2 is going to be our base, so we're going to make a function table. And we're going to use 5 simple exponents in place x. So we can graph. We use -2, -1, 0, 1, and 2. So we plug in each exponent into our function, we get 1/4, 1/2, 1, 2, and 4. As you can see, it will not cross the x-axis and will hit at 1 every time it goes to 0. Now when we graph this, just follow our points. And we can see that there's exponential growth. So now try one on your own. So let's try y equals 3x. Okay, so here you should have your table. Y equals 3x. So what value should have in here is 1/9 for -2, 1/3 for -1, 1 for 0, 3 for 1, and 9 for 2. And your graph should look like this. or close to this. So these are going to be your basic examples for an exponential function. You'll also see problems like graph and pair I equals 1/5 x. Y equals 6 1/5 x, and y equals maybe 2 1/5 x. So this is going to be a little bit different because here we're going to see a different way of graphing this. So since we have a fraction, the graph exponential is going to be an exponential decay rather than increasing. So here we'll see the graph start in quadrant 2 and go into quadrant 1 rather than starting in quadrant 2 and going into 1. So your graph for 1/5 will be normal, intersecting at 1. Y equals 1/5 x. For y, when we multiply the 6 to it, it'll start from the same point, but it will match up at 6 intersecting rather than 1. So it increases the rate. When we do -2, on the other hand, we'll see an opposite effect. We'll see that the exponential is in the opposite quadrant, going down. So now we're going to compare them. So we can see, compared to the parent graph of these three, that when multiplying a number to the function, it increases the rate of the y-intercept. So our y-intercept are going to be 1, and our original going to be 6, and y equals 6 1. And it will be -2. So these three numbers affect how the graph is going to be made. It doesn't change if it decays or not. It just decides the factor of the direction on the y-axis and the y-intercept. Now our final example is going to be word problem. So, So from start of the question, we can see according to Newton's law of cooling, the difference between temperature of an object and its surroundings decreases in time exponentially. So the problem says, suppose a certain cup of coffee is 95 degrees Celsius. Here we can see that now we have our temperature, which matches up right here in Newton's law. And is in a room that is 20 degrees Celsius. So here, 20 degrees Celsius is the surroundings stated in the law of cooling. So the cooling of the cup can be modeled by the equation y equals 75 parentheses times 75 times. So part A states find the temperature of the coffee after 15 minutes. So you're going to set up our equation. So 75 times 875 T. So there's our equation. Our first step is going to be plugging in time. So 75 from 875 15. We're looking for temperature of coffee after 15 minutes. And now we're going to multiply it out. Now 75 times 0.134 and finish up the equation and multiply these together, we'll get 10.12. So the difference of coffee is after 15 minutes is going to be 10.12 degrees Celsius. So in order to find the temperature of the coffee, we'll subtract it from 95, which is our earlier stated in the problem. We're going to subtract 10. And we should get 84.9 degrees Celsius is the temperature of our coffee after 15 minutes. So part B is asking to graph the function, the cooling function. So we can see it's going to be an exponential decay. So now we progress that up. So we know that the difference in the coffee was at 84.9. So that is going to be our y-intercept, which would be right about here. So we're going to start up, out. That's that, sorry. Oh, there, that's better. So we know that here is our temperature. So we know that on this end of the graph is before the cup started to cool. So these are where the original temperature started. Here is where our cooling starts for the equation, and this is how it exponentially decays according to function. So that is it. Thank you guys for watching.